We'll continue with Stefan Fiebeck's talk about auditing virtual appliances. Please go on.
All right, welcome everybody. I'll talk a little bit about the security of appliances, in specific virtual appliances. I'm Stefan Fiebeck. I'm security consultant with SecConsult here in the Vienna office. Some prior research includes some rootkit I wrote together with Wolfgang Ettlinger, who is right over here. Some insecure Wi-Fi passphrases used by popular ISPs in Austria and Germany. And I was the one who found the Wi-Fi protected setup vulnerability design flaw thing a while ago. Okay, and what's important, most of this stuff was done together with Wolfgang, so he knows basically the same thing as I do. I'm giving the talk, he's listening, so but he also did a great job there. Okay, so what's this talk about? I wanna discuss some analysis techniques specific to virtual appliances, but also some general techniques used for Linux systems, and raise awareness about serious vulnerabilities in appliances in general. So we'll talk about getting a root shell on appliance, which is the first step of the analysis process. Then analyzing the hardening state or general configuration state of the system, and then we'll move on to the meat, to the actual application that run on the appliance, and then I'll share a few thoughts about incident response, risks involved with using appliances, trusting appliances, and stuff like that. So what's an appliance? Basically, it's nothing magical. It's just a Linux system or some other open operating system running a lot of open source software and some proprietary applications. That's the applications you actually pay for. The rest is open source. Most of the vendors don't want you to know that it's just Linux and just Samba and just Apache and Java and stuff like that. So they try to kind of mask it, but so if you peek a little behind the curtains, it's just regular stuff you see on a daily basis. Here's some example products, example vendors. Almost all major vendors now offer these virtual editions of the hardware appliances. So the list goes on and on and on. And yeah, so why would you like to use a virtual appliance? Of course, it's fast deployment, it's easy configuration, all the cool stuff that comes with using virtual machines. No hardware, cool. Same thing goes for vendors. They don't have to offer hardware. They don't have to have people on the ground who do on-site support, fix hardware components and stuff like that. So maybe it's more money. I don't know. Could be a reason. So there are a few problems the vendors have recognized. They involve the intellectual property and also the licensing of specific appliance features. So what they're trying to do is keep you from getting deeper access to the appliance. And so the things we've seen mostly involve kinds of encryption and obfuscation and stuff. But there's no in-depth security anyways, so it just takes you longer to find something cool. Yeah, it's nothing serious. So researchers, for researchers and attackers, virtual appliances are cool because, as opposed to medical devices, you can get them mostly for free for testing. Salespeople are happy to give them to you. Maybe they'll call you 10 times a day, but that's something you have to ignore. and it's a great system to do debugging, because once you've got root access, you have access to all the source code, all the binaries. You can change configuration, enable debugging, enable more error output, maybe use some kind of debugging, VMX stuff, and you can enhance the quality of the audit of the appliance times 1,000 or something. So what you can do is, once you've found critical vulnerabilities, you can also use the exploits on physical appliances, because they share the same code base. So getting root, first step. As I've said, usually you only have access to a web interface and maybe some encurses dialog or some kind of restricted command line interface, which doesn't give you the ability to run arbitrary commands. So what you want to have is a shell, and best case, a root shell. So now we are on to getting a root shell. I'm going to discuss some files that make up the virtual machine on the VM host side. So there's this VMX file, there's this VMDK file, which is the disk, the hard disk in the virtual machine, and there's the VM files, VMem files. The VMem files are very interesting. They are a one-to-one image of the physical memory. So this is like the stuff that's on the RAM on your mainboard. It's used for snapshots of running systems, and also for storing the physical memory when you suspend the VM. And so now we are going on to using these different attack vectors, starting with the disk attack vector. So this is the most simple thing. You take a VMDK, mount it. You have access to all the data on the disk. So the physical equivalent would be to disassemble the appliance, take the hard disk, put it in another computer, and change stuff on the disk. So what's the things you want to change? It's the password file, the shadow file, sudoers file, all of that. If the hard disk is not encrypted, you're done at this point. You have a new user which has root privileges or the ability to sudo and stuff like that. So this is the easiest way, and this way it works for most appliances. But there are other ones which use encryption. So the ones I've seen use Lux and loopAS, and they're using some kind of modified versions of it, because they have the problem that the passphrase for the decryption of the AES master key has to be present at the time of boot. So this is something shortly after grub, or something in context of the kernel reboot. And the vendor isn't present to enter this key for you, so they have to somehow do a trick. And what they're doing is they use a hard-coded key and somehow obfuscate the mechanism to deobfuscate it, all kinds of that. So this is just security by obscurity. And if you spend some time reverse engineering, debugging the code, you'll find access to the passphrase, and then can go on and decrypt all the other volumes. So now I have a little example. This is the hard disk of F5 Firepass. As you can see, only the first partition is recognized. The others are unknown. In this case, they are encrypted. And on the first partition, you're going to find some interesting files. So this is LO setup and GPG and rootkey GPG. So they're using loopAS. Rootkey contains the AES master key and is encrypted using a passphrase, which has to somehow magically be entered into the GPG prompt. And the way that F5 has implemented this is they've changed LO setup to use the passphrase file descriptor parameter. So they're passing a file descriptor to GPG, and the parent process then writes every single character up to a new line into this file descriptor. And at this point, the GPG process has the full passphrase and can go on to decrypt the GPG file. So what I've done is some dirty patching. So I've re-enabled the standard error output and added some code to the GPG binary to basically print the passphrase once it's fully retrieved. And then call jump then use the jump dollar instruction to go into an endless loop. So this is really, really dirty stuff, but it works. And I have a short demo. So this is the virtual machine running Firepass. It starts to boot. And the font is too small to actually see something, but it doesn't matter at this point. So what we're seeing here is the boot process has stopped. So this is this endless loop, and the last line that was printed contains the AES, the passphrase used for the decryption of this GPG file. And now I can go and type, using visual recognition, type each and every character of the string, and can decrypt the other partitions, and yeah, remove some other stuff that makes getting a proper shell harder. And yeah, so this way we have a root shell and can go on with the other analysis. So in the Firepass we find a ton of PHP files which look like on the bottom left. So the left is a hex editor view. So we've got basically garbage, encrypted garbage. And when we go ahead and try to analyze these PHP files, or rather the programs that use these PHP files, we're going to find out that they're using GPG and a static key, and the decryption takes place in libphp. So Apache uses libphp, the modified F5 version of libphp, and every time a PHP file is evaluated, they decrypt it for evaluation. So this is the way they are doing this. And the nice thing about the nice thing is if you implement the decryption yourself, you can get full PHP code with developer comments and all of the nice stuff. Of course, this enhances the quality of the analysis, as I said. And we've also found, several vulnerabilities, and this was a while ago. So another route would be to use the physical memory way. So as we've discussed before, the VMem files are a one-to-one dump of the physical memory, and we can manipulate this file. So the physical equivalent for this attack would be these kinds of DMA attacks via FireWire and other components or buses. Coldboot, not really. Okay, so what we thought about is other people have implemented this for FireWire, where you can plug a FireWire cable into another laptop and do some pattern matching, patch some authentication code, which in a way that it always returns true. So you can enter any password, you can log in. This works for some Windows versions, some Ubuntu, whatever versions, but we found out that it's hard to find generic patterns and generic patches which work across years of Linux kernel, other Linux component code. So this is a bit hard. Then we had another thought, which was we could just go and patch shellcode anywhere in this VMem file and hope that it gets executed by a process that has root privileges or is the kernel, which is kind of a shotgun approach and should work at some point in time, but it's not reliable. And another, yeah. So this was the first ideas we had. One thing about this VMAM file is it doesn't contain all the information to map to get access to the virtual memory of processes. So maybe I can take you back to the university or something. So we've got paging. Paging is a problem in this case. On the bottom right, we see that the physical memory has no blue lines going back to the virtual memory. That's because we are missing some critical information, like the value of the CF3 register. So this is a register specific to each process, which points to the bottom of the page dictionary, and parts of the virtual addresses are used as indexes, and yeah. So this is how paging works. It doesn't really matter at this point, but in fact we can't go back without knowing information about kernel structures or some really smart way to find values of CS3 registers used in the context of the kernel. Another problem is, so another fact for the VMAM file is, if you look at it, it's just 4K blocks in basically random order. You've got everything in there, but maybe you get a page of kernel memory, a page of process A, a page of process B, and then so this is totally random from an outside view, and so this is hard to get the mapping, the backwards mapping. We did it in another way. So we wanted to batch the VMAM files. We did it the easy way. We didn't want to batch code. We wanted to batch data. So what we are doing is we are using the disk cache feature, which is a performance feature which caches files in memory. So the thing is, if you read a file twice, it will only result in one actual access to the hard disk. The second read is served from the cache file, from the cache memory. So once the password file has been accessed once, we can find a copy in the memory and modify it. The same goes for shadow, pseudos, all of that. So this way we can manipulate these files to add new users, change passwords of users, remove passwords of users, add users to the pseudos file, and all of that. So we have some tool, we don't have a name for it, but we will have eventually, which basically is an optimized web. So we go through each and every page, look at it, look at the start, and look at it, check if it's ASCII. So, and then we get the string until the first 0 byte, and apply our regexes, which identify if it's shadow, pass-specifier, all of that. So here's the generic approach we will take. So just suspend the VM, use our tool to dump the files, then add to the files a new user, use a proper shell, you add a hash to the shadows file, add the user to the pseudos file, and again use the tool to persist the changes back to the VMAM file. Then we can resume the VM, and now we can log in via, depends on the configuration, via SSH telnet or at least via the terminal. Okay, so here's a short demo. This is just a standard Ubuntu server. We are trying to log in as root, which doesn't work. Login incorrect. Then we are going to suspend the virtual machine and use our tool. So the output is not that, not that important actually. So this tool scans through the VMAM file and dumps 2 files. In this case, it's passwd and group. The other files haven't been used, so shadow hasn't been used at this point or something like that. And now we can go and remove the disabled flag from the root line in the bus.pd file. Save the file and then use the persist parameter to save the changes back to the vmem file. And now we can resume the VM and try to log in as root again, this time with no password prompt, and we are in. So this is the general way. And using this way, you can also add new users, can change passwords of users, all of that. So this is I can't think of a situation where you can't get in using this method. Okay, there's another attack vector which we've identified. I'm just going to touch it briefly. It's remote debugging. So this is the remote debugging feature that VMware implements. You can activate it using these lines. This is the physical equivalent of JTAG, so CPU level debugging, which results in 2 ports that are listening on localhost. And then you can go on and use GDB to connect to the CPU or to the VM and the different CPUs. So at this point, CPUs are just visible as threads so what you're seeing is a CPU context and not a process context. There are no symbols. So it's quite painful to use actually, but for analysis it can be useful. Okay, now onto the system state. So what we are trying to do when analyzing the basic system state is we want to expand access and escalate privileges and assume that we found some exploits in a component already. So let's say we've got command injection in the web application. So these vulnerabilities are useful for all kinds of post-exploitation and give you an idea about how the security posture of an appliance is. Yeah. So the baseline is, so what you would compare the results to is a usual, proper, configured, normal server in your usual environment. So if there are differences, you might not use this appliance if there are significant differences and deficiencies. So this can be partly automated and is not very time consuming. So what we are doing is basically the list of this and some other stuff. So we are looking at the privileges of services, look if there are some SVD binaries running, lying around, maybe some incorrect, improper folder permissions, file permissions. Yeah, so patch management is a huge issue in appliances. Vendors don't like to patch stuff because they now have to test stuff when they patch stuff, and they end up with 10-year-old libraries in their code, and so this is a huge problem. So you can go along and check which versions to use. Are they still up to date and stuff? The next thing I would look at is firewalling. Are there any services that shouldn't be there allowed to be allowed to be accessible from the network side? And another thing is backdoors. So these are remote access things that are implemented by vendors to provide support for customers. We've seen that a lot, and so if you think about it, it's of course it's not a good idea to use these things, and you might want to find out which kind of backdoor is in place, and then talk to the vendor. Maybe you can remove it, or you can configure your firewalls accordingly. And another one is backdoor and support accounts. So there have multiple instances of leftover accounts or accounts used by support on systems. And there have been some SSH pub keys lying around which are present, which are already in the release versions, which are already contained in the release versions of the appliances. So these are generated by the vendors. So let's move on to the application side. Here's a little graph thing containing the programming languages you're going to encounter. So this is nothing special. This is standard application security. So you're very likely to see web applications, some custom backend services, some proprietary services which are exposed to the local network or internet, and all of this code makes up the core functionality of the appliance. This is the stuff you pay your money for. All of this can be used, can be done with standard techniques. So it's manual and automated testing. So we have a focus on manual testing, not so much automated testing, but because vendors already use automated testing and they fail. There's reverse engineering, of course, for binary stuff. Some proprietary protocols which can be fast. So it's the whole range. And this is the part that is really time consuming. So if you want to really audit an appliance from bottom up, it takes you months or years. But of course it depends on the target. So if you just want to find a lot of 0 days, you maybe can get away with using some fancy grabs and find your vulnerabilities this way, because there's a lot of code and it's generally not the best code. So a few hints from me for people who want to look at appliances, maybe. So the web applications are still the best way to get into the appliance. There are the most vulnerabilities are found in the web applications, and these are most likely exposed to the LAN or parts of the LAN and to the internet. And of course, using cross-site scripting and cross-site request forgery, you can trick internal users into executing the attacks for you. So, yeah, and there's a lot of old legacy code with very bad coding practices. Another hint is to enable all kinds of debugging output. So if you want to get behind all the complexity of the applications on the appliance, it helps to see which components talk to which components and a lot of that. And also the secret query log also reveals some information about the connections between single components, which action results in this and this and this query. So these kinds of questions. Okay, and another hint would be to find out how all these fancy Java, PHP frameworks work. They are very, very complex, and even the developers don't know how to use them properly. So it's a good idea to learn it yourself, and then find some obscure bugs. Yeah, that nobody would consider. Okay. So I'm going to share some thoughts about incident response and appliances, but before I want to show you a list of security appliances we've had a look at, and we've discovered critical vulnerabilities, or mostly critical vulnerabilities in these appliances. So this is just for. As you can see, these are not just some small vendors. These are the really big ones. They've got huge problems in regards of application security. And although they're usually at all of these security conferences and stuff, they don't have figured it out quite yet. Okay, so let's play a little mind game. Let's assume you are responsible for one or more security appliances, and one of them has been compromised. Here's the question: how and when will you find out about it? I'm coming back to this in a second. So the risks involved with using security appliances are quite obvious. They are in very prominent places in your network. They act as routers, they act as proxies, they act as some kind of tunnels. They are right in the middle of all the traffic, have even some private keys for CA certificates that are used internally. So this is a huge issue. So if some of these appliances, if one of these appliances is compromised, an attacker can get a lot of insight, a lot of information just by sniffing at the local network interfaces or sniffing between applications and stuff. So this is just contained in this appliance. The attacker hasn't the attacker doesn't have to leave the appliance to get more information. Also, they receive and contain very critical information. Just as I've said, there are CA certificates which are installed company-wide and used for SSL man in the middle. So these web filter solutions, web security solutions, which scan HTTPS traffic for malware, basically, have these private keys. So so for sure your web filter solution would have this private key contained somewhere on the hard disk. Also, there are passwords for other backward servers on the hard disk, and also the appliances generally do receive plain text versions of passwords for domain users. So let's assume you set up your MDM client on your mobile device. You enter your domain credentials. The MDM receives the domain credentials, passes it on to the LDAP, all of that. But at some point in time, the MDM has the plain text version of your domain password. And of course, there are lots of privacy issues concerning these proxy solutions, filter solutions, regarding browser cookies and all of that. So from my point of view, security appliance is the perfect staging ground for further attacks. They are effectively a black box. There's no monitoring. You can't compare the state of an appliance to any known good state because you don't even know what services should be running and which shouldn't be running. So this is impossible for anyone except the vendor to know what should be there. And of course, administrators don't have root share. So how would you find some malware, some intrusion, if you don't even have a shell on the device? The problems. Okay. So again, back to the sinking ship. So how and when will you find out about the compromised security appliance? It's from my point of view, there's just two possibilities. I can't think of any more, but maybe you can. So when the attacker does something really, really stupid and reboots their appliance several times, maybe then the vendor support comes in and detects that something is running that shouldn't be running. That's a possibility. Or the appliance starts password brute forcing against some internal service or something like that, which can be traced back to the appliance. Another possibility is that the attack is at a very late stage, has already some financial impact, some obvious loss of intellectual property, which when it is, I don't know when this could be obvious, but still it's quite impossible to pinpoint this back to one single appliance which is insecure. So it's either never or when it's far too late. Okay. Good. So I'm doing good in time. Here just some takeaways for security researchers. Basically, look at virtual appliances. They are very easy to get. They contain a ton of vulnerabilities. Vendors are happy to give them to you. And yeah, security management, this is the serious part. Expect your appliances to be insecure, contain critical vulnerabilities, maybe tons of them. Expect them to be compromised at this point in time. And yeah, so do audit them, just like your network, your applications, your systems. And if you're installing a new appliance, go ahead and audit the appliance before you use it in production. This is going to save you a huge headache. Okay, and vendors, this is obvious. Do something, and if you're not already doing something, try a lot harder. Okay, thanks. That's it from me. Again, thanks to Wolfgang and all of the SecConsult teams worldwide, and of course you for being here. And yeah, thank you.
Are there any questions? None?
I'll try to put up the slides and the tool on a blog in the next days. You can pre-process. Okay, thank you.
Okay, thank you. Yeah?
The tool available in source code, or?
Yeah, sure. It's just maybe 100 lines of Python. It's nothing special, really.
Well, thank you very much for your talk.